episode of the physics tutorial. Okay, now I have a question here. There is a question on gas law. Before I take this question, let me quickly intimate you with gas laws. So we have different gas laws, and these gas laws are just relationship between some certain parameters, or some we call them physical quantities of a gas. So like the pressure, the volume, and the temperature. So we have the Boyle's law, which states that the pressure is inversely proportional to the volume, or volume is inversely proportional to the pressure, provided the temperature and number of moles of the molecule of the gas remain constant. So that means T is kept constant. T is equal to a constant. This is a constant value, and in this case we are going to have P equals to KV, where you have PV equals to K, is what will result into P1 V1 P2 over V2. This is a equation for Boyle's law. Also, we also have the Charles law, where we relate the relationship between the volume and the temperature. In this, we say that the volume is directly proportional to the temperature, provided pressure remains constant. So in this case, we can say V, sorry, let me get a better marker. The volume is equals to KT. So K equals to V1 T1 equals to V2 T2. This is Charles' law. We also have the pressure law, which we call the Gay-Lussac law, and that is the relationship between the pressure and the temperature. So P is directly proportional to temperature. So we have, provided the volume is kept constant. So in this case, we have K T. So K equals to P1 T1 equals to P2 T2. So this brings me to a question, and that's SSC 2017, question 9. Question 9, I think 9C. It says, at the beginning of a race, a tire of volume, so V1, a tire of volume 8.0 times 10 raised to power minus 4 meter cube at 20 degrees Celsius. T1 is 20 degrees Celsius. Remember that whenever you are solving equations or gas laws or problems, you have to convert this degrees Celsius to absolute temperature by adding. So this will give us 20 plus 273, and that is 293 Kelvin. So that's our T1. Then, as a gas pressure of 4.5, so gas pressure of 4.5 times 10 raised to the power 5 Pascal. Calculate the temperature of the gas. So we are calculating the temperature of the gas at the end of the race. If the pressure has risen to, if the P2 has risen to 4.6 times 10 raised to the power 5 Pascal. So this is a question, and for this question, it is very simple. You can see the tire has a fixed volume. So this is a kind of application question. They have given you V1. This V1 is also equal to the V2. So since V1 is equal, because the volume of the tire does not change. If you have a car tire, the volume of the car tire does not change. throughout the journey. So at the beginning of the journey, it was V1. So it will still remain V1. So that means V is kept constant. And out of all these laws, which law has V to be kept constant? That is the pressure law. I hope you have put me it. Pressure law. And in this case, we have we have P1, T1, P2 over T2. And so for this kind of question, we're going to impute our formulas. So we have 4.5 times 10 raised to the power 5 Pascal over 293 equals to P2 is 4.6 times 10 raised to the power 5 Pascal over T2. 5 Pascal cancels 10 raised to the power 5 Pascal. And now we're going to have so T2 equals to 293 times 4.6 divided by 4.5. So we have 293 times 4.6 divided by 4.5. And this gives us 299.5 Kelvin. 299.5 Kelvin. And if you're going to convert this to the degree Celsius of it, you're going to remove, so 299.5 minus 273. So minus 273 gives us 26 is 26.5 degree Celsius. So these are the equivalent temperature in Kelvin and degree Celsius. Also, if you have used a student that makes use of P1 V1 over T1 equals to P2 V2 over T2. This is the general gas law. If you use this general gas law equation, we are still going to mark you, because by the time this volume remains constant, V1 is equals to V2. It cancels out. So you still get your answer, the right answer. So then the second question, it's a table. You have a table like this. I have a table, resistance. This is resistance in ohms, and this is pressure in Pascal. Resistance in ohms, pressure in Pascal. This is the ice point, and this is the steam point. And we were told for the ice point, which is 270, sorry, I think this is ice point 273, steam point 373 Kelvin. So they are in Kelvin. Now for the ice point, we have 5.67, and the steam point, we have 7.75. Also, we have 7.13 times 10 raised to the power 4 and 9.74 times 10 raised to the power, I think it's also 4. So the question reads thus that the table above shows readings of the resistance and the pressure of a platinum resistance thermometer. So we are comparing this question is all about comparing two thermometers together. We are having the resistance thermometer, which is the platinum thermometer, and we have the pressure thermometer being compared with each other. So, and when immersed in the same liquid bath, use this data to determine the temperature of the bath on the resistance thermometer. This is the resistance thermometer, and this is the gas thermometer. Because pressure, if you have understood the physical property of a gas thermometer, or gas thermometer is what we call pressure. So changing the pressure of the gas. So that's why we say on the gas thermometer. When the resistance and the pressure So they have given us the resistance and the pressure are when the resistance and the pressure are. So for resistance R theta, we have 7.43 ohms, and on P theta, we are having 9.33 times 10 raised to power 4 Pascal, respectively. By what percentage is this temperature measured on a platinum resistance thermometer in error? So this question is so dynamic, and for someone that understood how to compare thermometers. So the first thing is, let's look at the resistance thermometer. This is resistance thermometer. This is the pressure, or we call it gas thermometer. Gas thermometer. So there are two thermometers we are dealing with now. Now for the resistance thermometer, we are given the higher the resistance thermometer, the steam point is this. So we can draw a line. The steam point is 373 and 273. So when it is at 373, you have 7.75, this in ohms. And when it was at 273, we have 5.67 in ohms. And we were told that what temperature will it give us? What's the resistance temperature we will have when it is at 7.43 ohms? So this kind of question, you should remember that I always tell my students there's a small code that we can use. The small code is to do something like this: upper minus lower divided by middle minus lower. So we're going to have something like this: 7.75 minus 5.67 divided by 7.43 minus 5.67 equals to 373 minus 273 divided by R theta minus 273. So upper minus lower divided by middle minus lower, upper minus lower divided by middle minus lower. So let's press our calculator. We're going to have something like this. So we have 7.75 minus 5.67 gives us 2.08. We have 2.08 divided by 7.43 minus 5.67. This gives us 1.76 equals to, this is 100 over R theta minus 273. If we cross multiply, we are going to have, this is 176, 2.08 times R theta minus, let's multiply 273 by 2.08 minus 567.84 equals to 176. So R theta equals to 176 plus 567.84. So plus 176 gives us, this is 743.84 divided by 2.08 divided by 2.08. So we have a value of let's check these values very well. 7.75, then 43, 7. Okay, 5.67. Okay, so 7.75 minus 5.67 equals 2.08. Okay, I can even do it another way. Where is the duster? So if you don't understand this way I've done it, I can find my value here. So I have 2.08, 7.75 minus 5.67 divided by 7.43 minus 5.67, and that gives me 1 point. This gives me 1.8. Sorry, let me change the marker. I'm not filling the marker again. Hope there's no problem. Okay. Um. Put on this. Okay. So are you on now? Okay. Let's quickly do this for to be out of time. So I have. Okay. So here's the calculator. So 2.08 divided by this give us, we have 1.182 equals to 100 over r theta minus 273. This method is not good enough. Okay, so with this now, we can cross multiply. If we cross multiply, you have r theta. So r theta minus 273 equals to 100 divided by, so 100 divided by 1.182 will give us, we have 84.602. So r theta equals to this plus 273. That gives us 357.6 ohms. Now, no, this r theta, okay, that's 357 ohms. But if of the fast gas laws, so what you just need to do here is to say, okay, this is 373, 273. This is the theta we are looking for, the gas pressure. We have a 7.75 ice point. So this for gas, okay, we have 9.74 times 10 raised power 4 and 7.13 times 10 raised power 4, and this is 9.33 times 10 raised power 4. So this case, you can just do this minus this. So 9.74 minus 7.13 all times 10 raised power 4 over 9.33 minus 7.13 times 10 raised to power 4 equals to 373 minus 273 over theta minus 273. So what we have here, this one cancels out this. This one cancels out this. So we have 9.74 minus 7.13. This gives us 2.61 over 9.33 minus 7.13. This gives us 2.2, which equals to 100 over theta minus 273. So we have, if you cross multiply this, that's 2.2 times 100 gives us 220. So we can say theta minus 273 equals to 220. Bring this one here, divided by 261. So divided by 2.61. No. 220 divided by 2.61, and that gives us 84.29, and so theta equals to 273 plus 84.29 plus 273, and this gives us 357.3 ohms. Now 357.3 ohms, and this for the gas pressure we had 357.6 ohms. For the resistance thermometer we had 357.6 ohms. For the gas thermometer we have 357.3 ohms. Of course, we know that the gas thermometer is more accurate than the resistance thermometer, because the most accurate type of thermometer is the gas thermometer. So now that means there's an error in this. This is 357.6 and this is 357.3. So there is an error of so let us calculate the error. The error here is equals to 357.6 minus 357.3 ohms, and that's giving us 0.3. So we have 0.3 as the error. So we were told to calculate the percentage error. The percentage error equals to the error over the original value, which is what? 357.3. That's the original, the real value, times 100. So if we do this, 0.3, 357.3 times 100, and this gives us a 0.084. That is the percentage error, 0.084%. So that's how this question is solved. So we have the R and we have the G theta here. So this is the question, this is the answer to that question. Also, in 2009, we also have a question that says that state the effect of an increase in pressure on boiling point and melting point of water. State the effect of increase in pressure on the boiling point and melting point of water. Now, we have to know that when there is an increase in pressure, surely we have what? Increase in the boiling point. When there is an increase in pressure, okay, let's look at it. Increase in pressure, increase in impurity. These two things, you have to note it. Increase in pressure increases the boiling point, increased boiling point, increased boiling point, and also it decreases the melting point. So decreased melting point. Increase in impurity. Also, when there is an impurity in a substance, it also affects the how will I call it? It affects the boiling point and the melting point of certain substances, and that's why you need to know all this. When impurities when impurity is added to a particular substance, it lowers its melting point. So this lowers melting point, this increases the boiling point. So when you put impurity, it increases the boiling point of, increase in pressure. Yes, increase in pressure as okay on the melting point, it decreases it. That's correct. So then for increase in impurity, it increases boiling point and also decreases what? The melting point. Okay, but this is not what I want to explain. There's a question that I need to also bring to your notice, and that is this graph, a graph of this. The graph went this way. Let me see. So we have something like this. 50, 100. This is 760. 760. This is 500. 760, 500. This is SVP. A graph of SVP against temperature. So the question says the graph above is that of a saturated vapor pressure, SVP of water against temperature. Pure water is known to boil at 100 degrees Celsius and at an atmospheric pressure of 760 millimeter of mercury. This is millimeter of mercury. What general conclusion can be drawn from the information given above? From the information given above. So the general conclusion that we can draw from this is that you will notice that it is at this point where the atmospheric pressure equals to 100 degrees Celsius. It's at that point that your water, your pure water, starts to boil. So at boiling point of pure water, the saturated vapor pressure of the water is equal to the external atmospheric pressure. And that's how to solve questions on this. Well, let's look at some other questions. Explain why it is not advisable to sterilize a clinical thermometer in boiling water. This kind of question is trying to test how much you understand the operation of a clinical thermometer and the function. A clinical thermometer is one thermometer that its range value is so small. It just starts from about 35 degrees Celsius to about maybe 43. So someone trying to use the clinical thermometer in a boiling water is definitely going to destroy the thermometer, because the thermometer cannot withstand anything more than about maybe 45 degrees Celsius. Else, the glass will break. So in that class, so the answer will be the glass will crack or burst due to excessive pressure created by expansion of the mercury, because as the mercury, as it's being heated up, the mercury keeps on increasing and expanding. So in the case of expanding, there's no space for it to expand because the range is just very small. Then it will break or crack or burst. So that is that about that. So then you have to also note how to solve questions when you're having a tube that is facing up. When it is facing up, remember that the pressure equals to atmospheric pressure plus this is the H. So atmospheric pressure plus this. If it is facing down, note that this will be pressure here will be H minus H. And if it is sitting horizontally, this will give us pressure 3 is what equals to the atmospheric pressure. So you have to note this particular principle, and that's what you're going to use to solve like this kind of question that says a thread of mercury of length 20 centimeter. Okay, let me see if I can quickly do something on that. A thread of mercury 20 centimeter, that's length. So the first length of 20 centimeter, this is the 20 centimeter. You put it here, 20 centimeter is used to trap some air in a capillary tube with uniform cross-sectional area and close at one end. Then with the tube vertical and open end uppermost. The length of the trap air is 15 centimeter. So this length of the trap air is 15 centimeter. In this case, our H, the H is 20 centimeter. Our L1 is 15 centimeter. With the two vertical and the open end, okay. The other case, calculate the length of the air column when the tube is held horizontally. So for case 1, when the tube is held horizontally, and that, so we can relate that this length is proportional to the volume. Since this length is proportional to the volume, so we can say that P1 V1 equals to P2 V2. So our P1, what's our P1? Our P1 will be the atmospheric pressure plus the we have been given the atmospheric pressure as H, which is 76 centimeter of mercury. So in this case, how we solve this question? We are using Boyle's law. So we are relating it, and in that case, what's the pressure here? Since pressure 1 is, since it's held here, so we are having 76 plus the height 20. So plus 20. So this is 76 plus 20 times V1. We relate it with 15 equals to P2 is what we are looking for. We are looking for the volume in this case, so the length. So we can just say, so we can even use V. So since the area is uniform cross-sectional area is equal, I can just say that P1 L1 equals to P2 L2. So that's 76 plus 20 times 15 equals to 76 for P2 when it's held horizontally. That means P2 equals to 76. So 76 times L2 is what we are looking for. So in this case, so L2 equals to 76 plus this, that's 96 times 15 divided by 76. And if we press that in our calculator, 96 times 15 divided by 76, this gives us 18.95 centimeters. 18.95 centimeters. So that's the length of the when it is held horizontally. But when it is held with the face down, so let us call this one P3. This is P2 now in this case. So we are having P3 equals to 76 minus 20. So that's automatically okay. So we will relate P1 V1 equals to P2 V2. No, P3 V3. So P1 L1 equals to P3 L3. So we're looking for P1 is already given to us 76 plus 20 times 15 equals to P3 is when it's held horizontally down. So 76 minus 20 times L3. So we have 96 times 15 equals to 56 L3. L3 equals to 96 times 15 over 56. So 96 times 15 times 56 divided by 56. So we have 25.71 centimeters. And this is how to solve this question. Like this, you have your full mark for solving it this way. So then let's see if we have another question. Now, a question can come like this. You have a displacement time graph. For a displacement time graph is a graph, a displacement time graph. This is year 10 or SS1 question relating to the first year in physics. So a question like displacement time graph. A displacement time graph is a graph of displacement in meters against time in seconds. So a displacement time graph is this kind of graph that you have displacement against time. And in this type of graph, the question says state two deductions that can be made from a displacement time graph. From a displacement time graph, we can determine the following. Number one, uniform velocity. Because velocity itself equals displacement over time. So while I have a slope, when I draw the slope, I can determine my velocity from the slope, given the displacement over time. Then also we can determine the instantaneous velocity. If it's not a straight line graph and it's a curve, if it's a curve, with a curve, we have something like this. We can determine the instantaneous velocity. Another thing we can determine is the initial displacement. So these are a few things we can determine from this displacement time graph. Now, let's look at a question. Dew point. What is dew point? Dew point is the temperature at which the water vaporize, or the water vapor or moisture present in the atmosphere or air is just enough or sufficient to saturate it. So, and you will see this, maybe you put a cold water in your bottle. This water was put inside the bottle, but because it's having contact with air around it, and the air around it, it condenses on this surface. That's why you see this water on this particular surface. It's not as if the water leaked out. So it is the air around it that cooled on that. That's dew. That's formation of dew. And we see it in our drinks, some of our drinks. So then the question says, explain why dew, let me read the question. Explain why dew forms more quickly on the metal part than on the rubber part of a bicycle placed in the open overnight. Now, this is very simple, and because metal is a better conductor, or is a better conductor of heat than rubber. So automatically at night, metal loses heat faster than rubber and becomes colder than the rubber. Unlike the rubber, it's not a conductor of it. So so warm air. Then the next thing you are going to say is that warm air gains latent heat, because the warm air around, they gain latent heat of vaporization from the from the metal than rubber, then you see dew forming on the metal parts more than forming on the rubber parts. So then what do you understand by two? Let me see. This question says, what is um, explain the statement. Specific heat capacity of copper is 400 joule per kilogram per Kelvin. Specific heat capacity of copper is 400 joule per kilogram per Kelvin. This means that copper requires 400 joules of heat. Then 1 kg of copper requires 400 joules of heat at every Okay. Okay. Sorry for the brain transition. The mic was off, so I have to connect it. So the when you're looking at the heat flux Q, this is the heat flux Q, which gives the rate per unit area at which heat flows in a given direction, and in this case, it is a minus direction. So in many of the materials, Q is observed to be directly proportional to the temperature difference. This is directly proportional to temperature difference, or we can say directly proportional to. So every every substance, are we there? So every substance has its own capacity for conducting and transferring heat. Uh, and we can explain this formula if we let's make this one our, okay, make K subject formula here. So if K is subject formula, we have QL over change in theta, and this Q, we can use the capital letter Q. This is flux, and this flux is the rate of the charge over area. So we can write QA over A. So where your K is the thermal conductivity in watts per meter per Kelvin, and Q is the amount of heat transferred through the material in joule per seconds, and that's in watts. So Q is in watts. The D or the L, sometimes you can see D. QD is also the same thing as QD over A delta theta or delta theta, but most times we use T for this. The D or the L is the distance between the two isothermal planes. Then the A is the area of the surface in square meters, while the delta T is the difference in the temperature. So we can find this Q. So whenever you are asked to find the thermal conductivity, the formula is just QD or QL over A delta T. There is a quantity of heat, the rate of heat, that's energy of heat, that's watt per watt in watts, joule per second. Then this one is the distance between the two planes. This is the area and this is the difference. So let's take a question. A question from WAEC. This is 2021 question. It says that let me draw the diagram. Yes, I'll be bringing this class one in very soon. So if you have not subscribed, you can kindly subscribe so that you can get more notifications Now, this question is WAEC 2021. And it says that define coefficient of thermal conductivity of a material. Define the coefficient of thermal conductivity of a material. So the coefficient of thermal conductivity of a material, we are not looking at the K. The coefficient, that's K itself is the thermal conductivity. That's it, is the time rate of flow of heat. The time rate of flow of heat, coefficient of thermal conductivity, time rate of flow of heat per unit area, per unit cross-sectional area, per unit cross-sectional area, per temperature gradient. And we can write that as QT over T equals to Ka change in theta or in T over change in L. So just like the one we wrote before, it's only the area that is missing here. So we have the change in theta, which is T here, and change in L. We also have the area. So that's the equation that we can use for such a question. Now, the question says that, let us take note of, the diagram illustrates a composite bar of iron and copper. The bar is insulated along its side and it has a diameter of 10 millimeter. We'll be doing all this conversion. The length and thermal conductivity, the length is 0.15 meter. Thermal conductivity is 40 watts per meter per Kelvin, respectively. And those of copper, this for iron, this iron. And for copper, we have, for copper is 0.05 meter, and K of copper is 360 watts per meter per Kelvin. If the free ends of the iron and copper are kept at 100 and 0 degrees Celsius respectively, calculate the temperature at the interface between the bars. This interface, we are looking for the theta here. The interface between the bars and the rate of heat flow along the bar. The rate of heat flow, that's this Q over T. That's what we are looking for in the second question. And for this kind of question, we can see that we have been given the K. So QT, let us first solve for the other one. So we have to equate the two together since they are having the same temperature at this place. So that means the QT, Q over T for iron is Q over T for copper. So we'll just start. K of iron is 40 times the area was given to us. That's area is pi r squared. The area equals pi r squared, which is the same thing as what? Pi d squared over 4. Pi d squared over 4. Change the, press the button. Press it again. Okay. So pi d squared over 4. Now, millimeter, we have to change this millimeter to meter. So if you are changing millimeter to meter, that's 10 times 10 raised per minus 3 meters. That's 1 millimeter. So in this case, we are going to put it into this formula. So area of this will be pi into d square. D square is 1, 10 times 10 raised to power minus 3 squared over 4, then times temperature, the temperature change. The temperature changes from 100 to 0 for iron. 100 to 0 minus 100, then the distance of the ion, the length of the ion is 0.15 meters, which is also equals to, for copper we have 360 times pi into, it's still the same distance. The area of this diameter of, let's find the diameter of uh, the diameter. I'm trying to look for the diameter of the bar is insulated with size, it has the diameter of this 10 millimeter. And okay, so in this case we are having, so it's the same diameter that we are using, 10 times 10 raised to power minus 3 squared over 4, then times 100 times 100 minus, this one is now theta, theta is higher, theta minus 0, theta minus 0 over the distance of that was given to us as 0.05. From here we know automatically that this we cancel out this, and this we cancel out this, pi we cancel out pi, then we have 40, this one we count here in 9 places, so we're having 100 over theta, 100 over theta over 0.15 equals to theta minus 0 over 0.05. So this is our resulting equation. So we can now find this. When you find that, let's find the, so this is so 0.15 divided by 0.05 is 3. So this one will go here 1, this one 3. So this becomes 100 minus theta equals to 3 theta. So this comes here, we have 100 equals to 3 theta plus theta. Then that's 4 theta. So 4 theta in 100, so we can find this, okay, 100 minus theta. So 4 theta, 100, that theta will give us 25 degrees Celsius. So it was maintained as 25 degrees Celsius, that's the theta. Then the other question says that the rate of flow along the bar, we can find that by just substituting our values for theta into this. So when you finish all this, the theta should give you 3.6. Okay. So you can read more about it. Because of time, I cannot dwell more on this area. Move to this side. Let me quickly, I think, let us end here because of time. Thank you for watching. If you have any questions, you can kindly send a message on the comment section, and I will explain. Is there any other thing that's coming? Just give me a minute. Let me check for some things. Okay. And for the other class, so you may be asked to also do dimension. You have to know dimension analysis. Um, I hope you still remember that there are properties of wave. Properties of wave. You have to know those ones too. Because we have the five properties of wave: reflection, refraction, diffraction, interference, and polarization. You have to know where the wave is plane polarized. So all these things are few things you have to know. Thank you for watching. See you in the next class. If you have any question, please comment. Send your question on the comment section. If you have any idea, observation, please put it on the comment in the comment section. Subscribe, like, share, and also uh, keep following us. Press the subscribe button. Thank you. Have a wonderful day. It's nice seeing you, Edge Academy.